No, the new method is certainly faster. So the current process, you take the calcium fluoride, the rocks, and you add them to boiling sulfuric acid in a rotary kiln. And remember, when you're doing that, you have to get a complete reaction. The HF then has to be trapped and then stored and then converted. This is a solid that can be made, a powder that can be made in, well, like 3 hours, and then you add it into a reaction to make a fluorochemical. So it is indeed faster in that sense. However, I would be very hesitant in saying that because the fluorochemical industry is a big industry and HF is still a very important molecule and important chemical. So there's definitely a lot of work to do in terms of taking that to something that's scalable to then be used by millions of people. Yeah, I wish I had a smart answer to this. It was a lot of trial and error. So we, as I showed, I think, we hypothesized that you could form potassium fluoride and a calcium phosphate salt. So I immediately was thinking, there must be a potassium fluoride salt involved. There must be a calcium phosphate salt involved. And so by taking those individual salts, ball milling them together, you could form these other salts X and Y. And then you can kind of see, those peaks match with the peaks in the diffraction pattern. So that's how I sort of split them up, if you will. Yeah.
So you produced salts that obviously didn't overlap as well?
Yeah, a lot of them.
A lot of them.
This is a great question. Because I guess then you would just be relying on, I guess, the friction and the grinding of the small little crystals in there. You do rely on the ball. So, in fact, we've done this control experiment that you're talking about. There isn't enough energy because you require the ball to collide with the solid. And in doing this, the ball moves through the solids in a figure of 8. So as you're shaking, that ball moves through. And it actually causes localized heating in the jar. So that might be one reason why some of the reaction's happening. The other thing is you do need something in there to grind to increase that surface area. So, yeah, thank you. So it's really all about balance, right? So energy efficiency then depends on how much energy does this ball mill take in comparison. That really requires a kind of deeper understanding, I think, from an economics point of view as well. And cheaper, certainly could be. Phosphate currently is more expensive than sulfuric acid. Sulfuric acid is one of the cheapest chemicals. But that's not to say, in 10 years, it might be the other way, where phosphate becomes cheaper than sulfuric acid. So it really depends on that. It's a very good question. It's a very complicated answer as well. But for now, this is definitely a first step into something that is more sustainable than the current process. Thank you. Great question. I get asked this a lot. So yeah, how do you convert this into something that's going to make kilograms of fluoromix? So there's a lot of work being done in mechanochemistry at the moment. So Veronique has actually started a startup company based on this research, where they're actually scaling up this technology. And one way of doing that is by passing these solids through screws. So it's called twin screw extrusion. So I'm talking to like an online audience, but yeah, it's called twin screw extrusion, where you put the powders into what I can only describe as like a mill used for bakeries, so used to grind flour. If you think about it, we're just grinding things. So a lot of the technology already exists, the same technology that's used to grind cement, to grind flour, to grind grains. So we can use that type of technology to scale up the chemistry. Yeah, that's a great. I've been thinking about that a lot. So now I'm at the end of the PhD, I do think like, what part did I enjoy the most? I have to say, I think it was definitely the kind of the collaborative work, finding the X and Y from the diffraction pattern. That I was scratching my head on for a long time, and that was really frustrating because you have something in front of you, you're like, wow, what is that? But not knowing what that was difficult. But it required working with a team, professors here in the inorganic department actually, and really good scientists to understand what those things were. So I'd say it was the kind of unexpected discoveries. That's my best part, I think, of the PhD.